Carry on with part 2. So color and appearance are the result of light interacting with an object. Light can interact with an object in several ways, including we can have selective spectral transmission or selective spectral reflectance. That means for transmission that the object absorbs some wavelengths of light and lets other wavelengths of light pass through it. That gives us a colored object that's transparent. If we have reflectance, some wavelengths are absorbed and some wavelengths are reflected, so that gives us a colored object that's not transparent. We can have selective spectral transmittance and spectral reflectance both in the same object. A lot of plastics are like that. That's an object that we call that's translucent, that light will pass through it, but also light will be reflected by it. Think of say a big McDonald's sign, the Golden Arches. All familiar with that. When we look at that object in the daytime, it has to look yellow, and we see the yellow that's reflected off of the surface because the light source is the sun. The light hits it on the outside and bounces off, and we see it. At night, what happens? Well, there's no outside light source. What they do is they turn the light on from the inside. So now that same plastic piece has to be transmitting light. It's not, I would say, completely transparent because you can't really see exactly through it, but it's translucent. That also has to look the same color yellow as the light comes from the back and comes through it. That's not always easy to do. Certainly not all pigments could do that. Look the same in reflective mode as in transmittance mode. Selective spectral absorption, so that's where it's absorbing certain wavelengths of light. Surface effects and specular reflectance. Remember we talked about how light bounces off the surface. If it has a shiny surface, it'll interact with light differently than if it has a matte finish surface. Remember which one, a matte finish or a shiny surface, which one looks lighter given everything else being the same, shiny surface or matte finish? So you know it's the matte finish because some of the specular reflectance can make it to our eye so it looks lighter. The surface effects, surface characteristics are very important in color matching if you want to match the color. If you get a standard that you have to match that's got a matte finish, and we're using our chips that we have in the lab, which is a shiny surface, you're going to have some of those effects that are going to make it appear different. Remember, there's color and there's appearance, and we're talking about the appearance when we talk about surface texture. The artificial system must model how the human color detection system works and give us the same results. The added benefit would be to eliminate the inherent variability of any human process. Whenever we do anything with people, there's definitely variability. There's variability with mechanical things and industrial things also, but generally people are much more variable than mechanical things. You know, just think of all the people you know and the variability in their abilities and their moods and their whatevers. Instruments usually don't have moods that you have to worry about. Even the same person is variable from time to time. You know, depending on what they're feeling like, what they just went through. They're not going to give you the same results when they're at their best as they are when they've been up for 3 days, just had a fight with their wife, and ran over their dog on their way to work. You know, they're not going to be in the same mood there and give you the same results. Our basic model for measuring color includes our 3 parts for perceiving color that we've talked about many times. You have to have an illuminant, object, and observer. Our mathematical functions of the standard observer allow a spectral graph to be converted into 3 numbers known as capital X, Y, and Z, or tristimulus values. So we're replacing our eye now with the standard observer, which remember was 3 curves that represented kind of how our 3 different cones in our eyes interact with light. You can calculate from that tristimulus values, which are capital X, Y, and Z, and those values identify a color we see, or the color we perceive, described by just these numbers over here, this X, Y, and Z values right there. And that represents a certain color. And the thing to keep in mind is that the light source is part of that calculation. So if we were to change the light source, this happens to be daylight, we changed it to artificial light or a tungsten light, which is just a light bulb, these numbers would change. Even though the object stays the same, standard observer stays the same, these numbers would change because the light source is part of the color. The problem with X, Y, and Z is that those numbers don't mean very much to us by themselves. And that's why we change them into numbers like LAB, and there's other numbers that we use that we'll talk about as we go along here. Daylight, artificial light are pretty consistent, but there's a ton of fluorescent lights that can be different. And not only different manufacturers, after a while they start to wear out. In industry, they measure the lights every so often to make sure that they're given the same results. There's calibration you can do, and there's also numbers on how long you should run them before you got to change them. We don't change ours until they burn out. You know, in industry, it's much more critical that you have exactly the right light source. But yeah, those things can cause differences. Does it make a big difference? Yeah, not really. And does it affect everything? Not so much. But there are certain critical applications where that can make a big difference, especially if you're talking about automotive. They're real picky about stuff. Again, while these numbers identify colors, unless you have an incredible memory for numbers, they're not very useful. They have to be converted into those other numbers we talked about. Tristimulus values are used to calculate several other variables used to describe color. There are many different types of calculations that have been performed and used, and we will concentrate on the ones that are most used in the industry. There's a lot of academic numbers that are out there that aren't used very much that we're not going to talk about. And there's even some industrial calculations that are used a little bit, but not very commonly, that we won't talk about. If you're interested in those calculations there, if you look in the textbook for this class, not the Munsell one, but the Bill Meyer book, there's lots and lots of calculating in there that you're more than welcome to spend your time on. I'm not going to go in. So the things that I don't talk about from the book, don't worry so much about. The things I talk about is what's important in industry and what we find important. There are a couple different LAB systems that are used in industry. One is called the Hunter Lab system, and the other is the C-Lab system. Both are commonly used in industry, although the Hunter LAB isn't used as much anymore as the CIA. Most people use the CIE system, but there are some people that use Hunter Lab, so you need to be aware of which one you're using if you're working with an LAB system. The Hunter system, like I said, not as commonly used as it used to be. That's still used. I know of a few companies that specifically use that Hunter system. The confusing part is both of them use LAB for their variables. The official designation that tells them apart in industry, most of the time those things are left out. But if you just see LAB like that, officially means the Hunter Lab system. If it has asterisks after those letters, that means the C-Lab system. In most cases, even if people are talking about C-Lab, they forget the asterisk. And I know when there's places in my stuff that does that too. Most of the time, assume we're talking about C-Lab unless we say something else. Just be careful that you're sure of that when you're doing those numbers. There's different calculations for both of those systems. So these are the calculations for LA and B that are used for the Hunter system. Notice that all the variables on the right sides of the equal signs are your tristimulus values, capital X, capital Y, capital Z. These are pretty involved equations. These aren't equations that anybody generally does. This is something a computer does. You don't have to calculate LAB numbers. There's not much point in that since computers do that. Now you look at these numbers, kind of a little bit idea how you calculate them. Then if we switch to the C-Lab system, you know, it's got the little asterisk there, they use also the X, Y, and Z tristimulus values to calculate it, but they use different equations. If you're using one type or the other type with the same X, Y, and Z or tristimulus values, you'll get different numbers for LA and B. And they're not going to be wildly different, but they will be different. So you can't correlate the two. You can't have some Hunter numbers and some C-Lab numbers and then put them together and see what you got. You have to be one system or the other. So we have our L, A, and B numbers, and also we have C for chroma, H for hue, and notice there's tangent and arctangent. I'm sure you're all familiar with those terms. It shouldn't be any problem calculating that. But again, these aren't numbers that you're going to have to calculate. If you ever wondered what you could use trigonometry for, if you've never had it, that's what those things are. Those are trig functions. And actually, if you have a fancy scientific calculator, all you do is hit the right button and you get it. And it's just a function. It has to do with angles and that sort of stuff. C-Lab color space can be graphically represented in three-dimensional space with two possibilities for the three dimensions. So we can describe our color and place it into our three-dimensional color space. Think of that model we had of the Munsell system that had kind of the pages sticking out and going around in a circle. All the colors fell in a certain spot, certain location on that model. That's what we mean by color space, a three-dimensional space, just like we live in a three-dimensional space. So we can describe a position in that three-dimensional space two different ways. We can do it with L, A, and B numbers, or we can do it with L, C, and H numbers. We can pick a very specific spot in our color diagram using those numbers. That's just a mathematical representation. We can do that in our three-dimensional physical space too. We can pick a point anywhere in this room, have a grid where we have an x-axis, a y-axis, and a z-axis, pinpoint a certain position in this room or anywhere. Okay, so here's a picture of what that might look like using colors. We see that the center there where it's got U is the center of our diagram, white and black. That axis goes through it. Think of this plane of what we're looking at is A and B. Lightness and darkness comes out of that plane. And then we can have A in this direction, B in this direction, like a regular grid. So we can describe a position by, for instance, A is this number, whatever it might be, and B is this A and B. We would pick out a certain point there. Or we can describe it, that's using LAB numbers, or we can use C and H numbers. H would be this angle from A to where the line is that's coming out from the center. That's the hue. And then the distance from the center to the point that we're talking about is the C. The difference between rectangular coordinates, which is the A and the B, or polar coordinates, which is the C and the H. It's just different ways of describing a position on a grid. It's mathematically what we're doing. So we're talking about it in terms of color, but we're also using mathematical functions and mathematical terminology. Students always ask, well, why do I have to take this math class? Well, this is one of the reasons, because it's where all this comes from. Okay, here's another picture of an LAB. We call it an opponent coordinate system because we have two opposites. The A axis, the opposites are red and green. The B opposites are yellow and blue. And then we have the other opposites are light and dark, or white and black. So those are our three opposite coordinates in our system. So the numbers are numbers, but it also has color meaning. We talk about it. A positive A is red, negative A is green. Positive is yellow, negative B is blue. Here's another way of picturing that LAB space as a cylinder. Our center point from top to bottom, that's the lightness in the center, white, black, grays. The farther out we get from the center is how chromatic it is, and as we go around the circle, that represents the different hues that we can have. Starts in one corner at red, goes towards yellow, green, blue, back to red. In a circle. When we talk about colors, we talk about color circle. Here's another diagram that shows that in a little bit more three-dimensional way. Essentially, it's the same color space. The thing is, when we show the cylinder or this kind of orange-looking thing, is that when you put all the colors in there, it doesn't necessarily make a perfect circle. There's areas where there just can't be any colors because For instance, you can't have a really chromatic dark yellow, or you can't have a chromatic light blue. If you remember the Munsell pages or the Munsell model, you can see there's more material or more colors that are in the center of the diagram than out towards the top and bottom, the light and darkness areas. All right, so those are some diagrams or some pictures. C-Lab space. Talk about the actual numbers. First one is the hue angle. It's measured in degrees, starting with 0 at the plus A or the red direction and increasing counterclockwise. So I could give you a number in terms of degrees for hue angle, and you could find out what the hue of that color is. We start with red being 0, so yellow would be 90 degrees, green would be 180 degrees, blue would be 270 degrees, and then if we get back to 360, because the circle is 360, we're back at red again. 360 degrees in a circle, and all of those would represent a different hue. So we're talking about hue here. If we had a color that had a hue angle of 45 degrees, what color would that be? Orange, yeah. And if we had a hue angle of 225, that would be blue-green, green-blue, whatever. The closer it was to 180, the more green it would be. The closer it would be to 270, the more blue it would be. And then after we go past 270, it would start to be more red, less blue. That's one way of describing what the hue is by the hue angle. And here's a picture that shows that. 0 degrees there, 90, 180. And the calculation there, if you're interested, is you take the arctangent of the B value divided by the A value. And actually what that means is arctangent means, if you're interested, the angle whose tangent equals whatever that number is, B divided by A. And then you get a value for that. If you have, like say, a scientific calculator, you can calculate. The chroma is measured as the length of the line from the neutral point, and the neutral point is where A and B equals 0 on our diagram, and we're kind of, in these discussions, ignoring the L direction and just talking about A and B. Both of those equal 0, so we're at the center of the diagram. The farther out we get from the center, the more chromatic it is. We can calculate that number based on whatever our A and B values are.